Chapter 8, Part 3 of The Outline of Science. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. This recording is by Mark Smith of Simpsonville, South Carolina. The Outline of Science, Volume 1, by J. Arthur Thomson. Chapter 8, Part 3. Light, visible and invisible. If light, then, consists of waves transmitted through the ether, what gives rise to the waves? Whatever sets up such wonderfully rapid series of waves must be something with an enormous vibration. We come back to the electron. All atoms of matter, as we have seen, are made up of electrons revolving in a regular orbit round a nucleus. These electrons may be affected by outside influences. They may be agitated and their speed or vibration increased. Electrons and light. The particles even of a piece of cold iron are in a state of vibration. No nerves of ours are able to feel and register the waves they emit, but your cold poker is really radiating or sending out a series of wave movements on every side. After what we saw about the nature of matter, this will surprise none. Put your poker in the fire for a time. The particles of the glowing coal, which are violently agitated, communicate some of their energy to the particles of iron in the poker. They move to and fro more rapidly, and the waves which they create are now able to affect your nerves and cause a sensation of heat. But put the poker again in the fire until its temperature rises to 500 degrees centigrade. It begins to glow with a dull red. Its particles are now moving very violently, and the waves they send out are so short and rapid that they can be picked up by the eye. We have visible light. They would still not affect a photographic plate. Heat the iron further, and the crowds of electrons now send out waves of various lengths which blend into white light. What is happening is the agitated electrons flying round in their orbits at a speed of trillions of times a second. Make the iron blue hot, and it pours out, in addition to light, the invisible waves which alter the film on the photographic plate. And beyond these there is a long range of still shorter waves, culminating in the X-rays, which will pass between the atoms of flesh or stone. Nearly 250 years ago it was proved that light traveled at least 600,000 times faster than sound. Jupiter, as we saw, has moons which circle round it. They pass behind the body of the planet and reappear at the other side. But it was noticed that when Jupiter is at its greatest distance from us, the reappearance of the moon from behind it is 16 minutes and 36 seconds later than when the planet is nearest to us. Plainly, this was because light took so long to cover the additional distance. The distance was then imperfectly known, and the speed of light was underrated. We now know the distance, and we can easily get the velocity of light. No doubt it seems far more wonderful to discover this within the walls of a laboratory, but it was done as long ago as 1850. A cogged wheel is so mounted that a ray of light passes between two of the teeth and is reflected back from a mirror. Now, slight as is the fraction of a second which light takes to travel that distance, it is possible to give such speed to the wheel that the next tooth catches the ray of light on its return and cuts it off. The speed is increased still further until the ray of light returns to the eye of the observer through the notch next to the one by which it had passed to the mirror. The speed of the wheel was known, and it was thus possible again to gather the velocity of light. If the shortest waves are 1/67,000th of an inch in length, and light travels at 186,000 miles a second, any person can work out that about 800 trillion waves enter the eye in a second when we see violet. Sorting out light waves. The waves sent out on every side by the energetic electrons become faintly visible to us when they reach about 1/35,000th of an inch. As they become shorter and more rapid, as the electrons increase their speed, we get, in succession, the colors red, orange, yellow, green, blue, indigo, and violet. Each distinct sensation of color means a wave of different length. When they are all mingled together, as in the light of the sun, we get white light. When this white light passes through glass, the speed of the waves is lessened, and if the ray of light falls obliquely on a triangular piece of glass, the waves of different lengths part company as they travel through it, and the light is spread out in a band of rainbow color. The waves are sorted out according to their lengths in the obstacle rays through the glass. Anyone may see this for himself by holding up a wedge-shaped piece of crystal between the sunlight and the eye. The prism separates the sunlight into its constituent colors, and these various colors will be seen quite readily. Or the thing may be realized in another way. If the 7 colors are painted on a wheel as shown, opposite page 280, in the proportion shown, and the wheel rapidly revolved on a pivot, the wheel will appear a dull white. The several colors will not be seen. But omit one of the colors, then the wheel, when revolved, will not appear white, but will give the impression of one color, corresponding to what the union of 6 colors gives. Another experiment will show that some bodies held up between the eye and a white light will not permit all the rays to pass through, but will intercept some. A body that intercepts all the 7 rays except red will give the impression of red, or if all the rays except violet, then violet will be the color seen. The fate of the world. Professor Soddy has given an interesting picture of what might happen when the sun's light and heat is no longer what it is. The human eye has adapted itself through the ages to the peculiarities of the sun's light, so as to make the most of that wavelength of which there is most. Let us indulge for a moment in these gloomy prognostications as to the consequences to this earth of the cooling of the sun with the lapse of ages, which used to be in vogue, but which radioactivity has so rudely shaken. Picture the fate of the world when the sun has become a dull red-hot ball, or even when it is cooled so far that it would no longer emit light to us. That does not all mean that the world would be an inky darkness, and that the sun would not emit light to the people then inhabiting this world, if any had survived and could keep themselves from freezing. To such, if the eye continued to adapt itself to the changing conditions, our blues and violets would be ultraviolet and invisible, but our dark heat would be light, and hot bodies would be luminous to them which would be dark to us. What the blue sky means. We saw in a previous chapter how the spectroscope splits up light waves into their colors, but nature is constantly splitting the light into its different lengthed waves, its colors. The rainbow, where dense moisture in the air acts as a spectroscope, is the most familiar example. A piece of mother of pearl, or even a film of oil on the street or on water, has the same effect, owing to the fine inequalities in its surface. The atmosphere all day long is sorting out the waves. The blue sky overhead means that the fine particles in the upper atmosphere catch the shorter waves, the blue waves, and scatter them. We can make a tube full of blue sky in the laboratory at any time. The beautiful pink flush on the Alps at sunrise, the red glory that lingers in the west at sunset, mean that, as the sun's rays must struggle through denser masses of air when it is low on the horizon, the long red waves are sifted out from the other shafts. Then there is the varied face of nature which, by absorbing some waves and reflecting others, weaves its own beautiful robe of color. Here and there is a black patch, which absorbs all the light. White surfaces reflect the whole of it. What is reflected depends on the period of vibration of the electrons in the particular kind of matter. Generally, as the electrons receive the flood of trillions of waves, they absorb either the long or the medium or the short, and they give us the wonderful color scheme of nature. In some cases the electrons continue to radiate long after the sunlight has ceased to fall upon them. We get from them black or invisible light, and we can take photographs by it. Other bodies, like glass, vibrate in unison with the period of the light waves, and let them stream through. Light without heat. There are substances, phosphorescent things we call them, which give out a mysterious cold light of their own. It is one of the problems of science, and one of profound practical interest. If we could produce light without heat, our gas bill would shrink amazingly. So much energy is wasted in the production of heat waves and ultraviolet waves which we do not want, that 90% or more of the power used in illumination is wasted. Would that the glowworm, or even the dead herring, would yield us its secret. Phosphorus is the one thing we know as yet that suits the purpose, and it smells. Indeed, our artificial light is not only extravagant in cost but often poor in color. The unwary person often buys a garment by artificial light, and is disgusted next morning to find in it a color which is not wanted. The color disclosed by the sun was not in the waves of the artificial light. Beyond the waves of violet light are the still shorter and more rapid waves, the ultraviolet waves, which are precious to the photographer. As every amateur knows, his plate may safely be exposed to light that comes through a red or an orange screen. Such a screen means no thoroughfare for the blue and beyond blue waves, and it is these which arrange the little grains of silver on the plate. It is the same waves which supply the energy to the little green grains of matter, chlorophyll, in the plant, preparing our food and timber for us, as will be seen later. The tree struggles upward and spreads out its leaves fanwise to the blue sky to receive them. In our coal measures, the mighty dead forests of long ago are vast stores of sunlight which we are prodigally using up. The X-rays are the extreme end, the highest octave of the series of waves. Their power of penetration implies that they are excessively minute, but even these have not held their secret from the modern physicist. From a series of beautiful experiments, in which they were made to pass amongst the atoms of a crystal, we learn their length. It is about the 10 millionth of a millimeter, and a millimeter is about the 1/25th of an inch. One of the most recent discoveries, made during a recent eclipse of the sun, is that light is subject to gravitation. A ray of light from a star is bent out of its straight path when it passes near the mass of the sun. Professor Eddington tells us that we have as much right to speak of a pound of light as of a pound of sugar. Professor Eddington even calculates that the Earth receives 160 tons of light from the sun every year. Energy, how all life depends on it. As we have seen in an earlier chapter, one of the fundamental entities of the universe is matter. A second, not less important, is called energy. Energy is indispensable if the world is to continue to exist, since all phenomena, including life, depend on it. Just as it is humanly impossible to create or to destroy a particle of matter, so is it impossible to create or to destroy energy. This statement will be more readily understood when we have considered what energy is. Energy, like matter, is indestructible, and just as matter exists in various forms, so does energy. And we may add, just as we are ignorant of what the negative and positive particles of electricity which constitute matter really are, so we are ignorant of the true nature of energy. At the same time, energy is not so completely mysterious as it once was. It is another of nature's mysteries which the advance of modern science has in some measure unveiled. It was only during the 19th century that energy came to be known as something as distinct and permanent as matter itself. Forms of energy. The existence of various forms of energy had been known, of course, for ages. There was the energy of a falling stone, the energy produced by burning wood or coal or any other substance, but the essential identity of all these forms of energy had not been suspected. The conception of energy as something which, like matter, was constant in amount, which could not be created nor destroyed, was one of the great scientific acquisitions of the past century. It is not possible to enter deeply into this subject here. It is sufficient if we briefly outline its salient aspects. Energy is recognized in two forms, kinetic and potential. The form of energy which is most apparent to us is the energy of motion. For example, a rolling stone, running water, a falling body, and so on. We call the energy of motion kinetic energy. Potential energy is the energy a body has in virtue of its position, in its capacity, in other words, to acquire kinetic energy, as in the case of a stone resting on the edge of a cliff. Energy may assume different forms. One kind of energy may be converted directly or indirectly into some other form. The energy of burning coal, for example, is converted into heat, and from heat energy we have mechanical energy, such as that manifested by the steam engine. In this way we can transfer energy from one body to another. There is the energy of the great waterfalls of Niagara, for instance, which are used to supply the energy of huge electric power stations. What heat is. An important fact about energy is that energy tends to take the form of heat energy. The impact of a falling stone generates heat. A waterfall is hotter at the bottom than at the top. The falling particles of water on striking the ground generate heat, and most chemical changes are attended by heat changes. Energy may remain latent indefinitely in a lump of wood, but in combustion it is liberated, and we have heat as a result. The atom of radium or of any other radioactive substance, as it disintegrates, generates heat. Every hour radium generates sufficient heat to raise the temperature of its own weight of water from the freezing point to the boiling point. And what is heat? Heat is molecular motion. The molecules of every substance, as we have seen on a previous page, are in a state of continual motion, and the more vigorous the motion, the hotter the body. As wood or coal burns, the invisible molecules of these substances are violently agitated, and give rise to ether waves which our senses interpret as light and heat. In this constant movement of the molecules, then, we have a manifestation of the energy of motion and of heat. That energy which disappears in one form reappears in another has been found to be universally true. It was Joule who, by churning water, first showed that a measurable quantity of mechanical energy could be transformed into a measurable quantity of heat energy. By causing an apparatus to stir water vigorously, that apparatus being driven by falling weights or a rotating flywheel, or by any other mechanical means, the water became heated. A certain amount of mechanical energy had been used up, and a certain amount of heat had appeared. The relation between these two things was found to be invariable. Every physical change in nature involves a transformation of energy, but the total quantity of energy in the universe remains unaltered. This is the great doctrine of the conservation of energy. Substitutes for coal. Consider the source of nearly all the energy which is used in modern civilization: coal. The great forests of the Carboniferous epoch now exist as beds of coal. By the burning of coal, a chemical transformation, the heat energy is produced on which at present our whole civilization depends. Whence is the energy locked up in the coal derived? From the sun. For millions of years the energy of the sun's rays had gone to form the vast vegetation of the Carboniferous period, had gone to form the vast vegetation of the Carboniferous era, and had been transformed by various subtle processes into the potential energy that slumbers in those immense fossilized forests. The exhaustion of our coal deposits would mean, so far as our knowledge extends at present, the end of the world's civilization. There are other known sources of energy, it is true. There is the energy of falling water. The great falls of Niagara are used to supply the energy of huge electric power stations. Perhaps also something could be done to utilize the energy of the tides, another instance of the energy of moving water. And attempts have been made to utilize directly the energy of the sun's rays. But all these sources of energy are small compared with the energy of coal. A suggestion was made at a recent British Association meeting that deep borings might be sunk in order to utilize the internal heat of the earth, but this is not perhaps a very practical proposal. By far the most effective substitutes for coal would be found in the interior energy of the atom, a source of energy which, as we have seen, is practically illimitable. If the immense electrical energy in the interior of the atom can ever be liberated and controlled, then our steadily decreasing coal supply will no longer be the bugbear it now is to all thoughtful men. The stored up energy of the great coal fields can be used up, but we cannot replace it or create fresh supplies. As we have seen, energy cannot be destroyed, but it can become unavailable. Let us consider what this important fact means. Dissipation of energy. Energy may become dissipated. Where does it go? Since if it is indestructible, it must still exist. It is easier to ask the question than to give a final answer, and it is not possible in this outline, where an advanced knowledge of physics is not assumed on the part of the reader, to go fully into the somewhat difficult theories put forward by physicists and chemists. We may raise the temperature, say, of iron until it is white hot. If we stop the process, the temperature of the iron will gradually settle down to the temperature of the surrounding bodies. As it does so, where does its previous energy go? In some measure it may pass to other bodies in contact with the piece of iron, but ultimately the heat becomes radiated away in space, where we cannot follow it. It has been added to the vast reservoir of unavailable heat energy of uniform temperature. It is sufficient here to say that if all bodies had a uniform temperature, we should experience no such thing as heat, because heat only travels from one body to another, having the effect of cooling the one and warming the other. In time, the two bodies acquire the same temperature. The sum total of the heat in any body is measured in terms of the kinetic energy of its moving molecules. There must come a time, so far as we can see at present, when, even if all the heat energy of the universe is not radiated away into empty, infinite space, yet a uniform temperature will prevail. If one body is hotter than another, it radiates heat to that body until both are at the same temperature. Each body may still possess a considerable quantity of heat energy, which it has absorbed, but that energy, so far as reactions between those two bodies are concerned, is now unavailable. The same principle applies whatever number of bodies we consider. Before heat energy can be utilized, we must have bodies with different temperature. If the whole universe were at some uniform temperature, then, although it might possess an enormous amount of heat energy, this energy would be unavailable. What a uniform temperature would mean. And what does this imply? It implies a great deal. For if all the energy in the world became unavailable, the universe as it now is would cease to be. It is possible that, by the constant interchange of heat radiations, the whole universe is tending to some uniform temperature, in which case, although all molecular motion would not have ceased, it would have become unavailable. In this sense, it may be said that the universe is running down. If all the molecules of a substance were brought to a standstill, that substance would be at the absolute zero of temperature. There could be nothing colder. The temperature at which all molecular motions would cease is known. It is minus 273 degrees centigrade. No body could possibly attain a lower temperature than this. A lower temperature could not exist. Unless there exists in nature some process of which we know nothing at present, whereby energy is renewed, our solar system must one day sink to this absolute zero of temperature. The sun, the earth, and every other body in the universe is steadily radiating heat, and this radiation cannot go on forever, because heat continually tends to diffuse and to equalize temperatures. But we can see theoretically that there is a way of evading this law. If the chaotic molecular motions which constitute heat could be regulated, then the heat energy of a body could be utilized directly. Some authorities think that some of the processes which go on in the living body do not involve any waste energy, that the chemical energy of food is transformed directly into work without any of it being dissipated as useless heat energy. It may be, therefore, that man will finally discover some way of escape from the natural law that, while energy cannot be destroyed, it has a tendency to become unavailable. The primary reservoir of energy is the atom. It is the energy of the atom of elements in the sun, the stars, the earth, from which nature draws for all her supply of energy. Shall we ever discover how we can replenish the dwindling resources of energy, or find out how we can call into being the at present unavailable energy which is stored up in uniform temperature? It looks as if our successors would witness an interesting race between the progress of science on the one hand and the depletion of natural resources upon the other. The natural rate of flow of energy from its primary atomic reservoirs to the sea of waste heat energy of uniform temperature allows life to proceed at a complete pace sternly regulated by the inexorable laws of supply and demand, which the biologists have recognized in their field as the struggle for existence. It is certain that energy is an actual entity just as much as matter, and that it cannot be created or destroyed. Matter and ether are receptacles or vehicles of energy. As we have said, what these entities really are in themselves we do not know. It may be that all forms of energy are in some fundamental way aspects of the same primary entity which constitutes matter. How all matter is constituted of particles of electricity we have already seen. The question to which we await an answer is, what is electricity? Matter, ether, and Einstein. The supreme synthesis, the crown of all this progressive conquest of nature, would be to discover that the particles of positive and negative electricity, which make up the atoms of matter, are points or centers of disturbances of some kind in a universal ether, and that all our energies, light, magnetism, gravitation, etc., are waves or strains of some kind set up in the ether by these clusters of electrons. It is a fascinating, tantalizing dream. Larmor suggested in 1900 that the electron is a tiny whirlpool or vortex in ether, and as such a vortex may turn in either of two opposite ways, we seem to see a possibility of explaining positive and negative electricity. But the difficulties have proved very serious, and the nature of the electron is unknown. A recent view is that it is a ring of negative electricity rotating about its axis at a high speed, though that does not carry us very far. The unit of positive electricity is even less known. We must be content to know the general lines on which thought is moving towards the final unification. We say unification, but it would be a grave error to think that ether is the only possible basis for such unity, or to make it an essential part of one's philosophy of the universe. Ether was never more than an imagined entity to which we ascribed the most extraordinary properties, and which seemed then to promise considerable aid. It was conceived as an elastic solid of very great density, stretching from end to end of the universe, transmitting waves from star to star at the rate of 186,000 miles a second. Yet it was believed that the most solid matter passed through it as if it did not exist. Some years ago a delicate experiment was tried for the purpose of detecting the ether. Since the Earth, in traveling round the Sun, must move through the ether if the ether exists, there ought to be a stream of ether flowing through every laboratory, just as the motion of a ship through a still atmosphere will make a wind. In 1887, Michelson and Morley tried to detect this. Theoretically, a ray of light in the direction of the stream ought to travel at a different rate from a ray of light against the stream or across it. They found no difference, and scores of other experiments have failed. This does not prove that there is no ether, as there is reason to suppose that our instruments would appear to shrink in precisely the same proportion as the alteration of the light. But the fact remains that we have no proof of the existence of ether. J. H. Jeans says that nature acts as if no such thing existed. Even the phenomena of light and magnetism, he says, do not imply ether, and he thinks that the hypothesis may be abandoned. The primary reason, of course, for giving up the notion of the ether is that, as Einstein has shown, there is no way of detecting its existence. If there is an ether, then, since the Earth is moving through it, there should be some way of detecting this motion. The experiment has been tried, as we have said, but, although the method used was very sensitive, no motion was discovered. It is Einstein who, by revolutionizing our conceptions of space and time, showed that no such motion ever could be discovered, whatever means were employed, and that the usual notion of the ether must be abandoned. We shall explain this theory more fully in a later section. Influence of the tides. Origin of the moon. The earth slowing down. Until comparatively recent times, until in fact the full dawn of modern science, the tides ranked amongst the greatest of nature's mysteries. And indeed, what agency could be invoked to explain this mysteriously regular flux and reflux of the waters of the ocean? It is not surprising that that steady, rhythmical rise and fall suggested to some imaginative minds the breathing of a mighty animal. And even when man first became aware of the fact that this regular movement was somehow associated with the moon, was he much nearer an explanation? What bond could exist between the movements of that distant world and the diurnal variation of the waters of the earth? It is reported that an ancient astronomer, despairing of ever resolving the mystery, drowned himself in the sea. The earth pulled by the moon. But it was part of the merit of Newton's mighty theory of gravitation that it furnished an explanation even of this age-old mystery. We can see, in broad outlines at any rate, that the theory of universal attraction can be applied to this case. For the moon, Newton taught us, pulls every particle of matter throughout the earth. If we imagine that part of the earth's surface which comprises the Pacific Ocean, for instance, to be turned towards the moon, we see that the moon's pull, acting on the loose and mobile water, would tend to heap it up into a sort of mound. The whole earth is pulled by the moon, but the water is more free to obey this pull than is the solid earth, although small tides are also caused in the earth's solid crust. It can be shown also that a corresponding hump would tend to be produced on the other side of the earth, owing in this case to the tendency of the water, being more loosely connected, to lag behind the solid earth. If the earth's surface were entirely fluid, the rotation of the earth would give the impression that these two humps were continually traveling round the world once every day. At any given part of the earth's surface, therefore, there would be two humps daily, that is, two periods of high water. Such is the simplest possible outline of the gravitational theory of the tides. The actually observed phenomena are vastly more complicated, and the complete theory bears very little resemblance to the simple form we have just outlined. Everyone who lives in the neighborhood of a port knows, for instance, that high water seldom coincides with the time when the moon crosses the meridian. It may be several hours early or late. High water at London Bridge, for instance, occurs about 1½ hours after the moon has passed the meridian, while at Dublin high water occurs about 1½ hours before the moon crosses the meridian. The actually observed phenomena, then, are far from simple. They have, nevertheless, been very completely worked out, and the times of high water for every port in the world can now be prophesied for a considerable time ahead. The action of sun and moon. It would be beyond our scope to attempt to explain the complete theory, but we may mention one obvious factor which must be taken into account. Since the moon, by its gravitational attraction, produces tides, we should expect that the sun, whose gravitational attraction is so much stronger, should also produce tides, and, we would suppose at first sight, more powerful tides than the moon. But while it is true that the sun produces tides, it is not true that they are more powerful than those produced by the moon. The sun's tide-producing power is, as a matter of fact, less than half that of the moon. The reason of this is that distance plays an enormous role in the production of tides. The mass of the sun is 26 million times that of the moon. On the other hand, it is 386 times as far off as the moon. This greater distance more than counterbalances its greater mass, and the result, as we have said, is that the moon is more than twice as powerful. Sometimes the sun and moon act together, and we have what are called spring tides. Sometimes they act against one another, and we have neap tides. These effects are further complicated by a number of other factors, and the tides at various places vary enormously. Thus, at St. Helena, the sea rises and falls about 3 feet, whereas in the Bay of Fundy it rises and falls more than 50 feet. But here again the reasons are complicated. origin of the moon. But there is another aspect of the tides which is of vastly greater interest and importance than the theory we have just been discussing. In the hands of Sir George H. Darwin, the son of Charles Darwin, the tides have been made to throw light on the evolution of our solar system. In particular, they have illustrated the origin and development of the system formed by our Earth and Moon. It is quite certain that, long ages ago, the Earth was rotating immensely faster than it is now, and that the Moon was so near as to be actually in contact with the Earth. In that remote age, the Moon was just on the point of separating from the Earth, of being thrown off by the Earth. Earth and Moon were once one body, but the high rate of rotation caused this body to split up into two pieces. One piece became the Earth we now know, and the other became the Moon. Such is the conclusion to which we are led by an examination of the tides. In the first place, let us consider the energy produced by the tides. We see evidences of this energy all round the world's coastlines. Estuaries are scooped out, great rocks are gradually reduced to rubble, innumerable tons of matter are continually being set in movement. Whence is this energy derived? Energy, like matter, cannot be created from nothing. What, then, is the source which makes this colossal expenditure possible? The Earth slowing down. The answer is simple, but startling. The source of tidal energy is the rotation of the Earth. The massive bulk of the Earth, turning every 24 hours on its axis, is like a gigantic flywheel. In virtue of its rotation, it possesses an enormous store of energy. But even the heaviest and swiftest flywheel, if it is doing work, or even if it is only working against the friction of its bearings, cannot dispense energy forever. It must gradually slow down. There is no escape from this reasoning. It is the rotation of the Earth which supplies the energy of the tides, and as a consequence the tides must be slowing down the Earth. The tides act as a kind of brake on the Earth's rotation. These masses of water, held back by the Moon, exert a kind of dragging effect on the rotating Earth. Doubtless this effect, measured by our ordinary standards, is very small. It is, however, continuous, and in the course of the millions of years dealt with in astronomy, this small but constant effect may produce very considerable results. But there is another effect which can be shown to be a necessary mathematical consequence of tidal action. It is the Moon's action on the Earth which produces the tides, but they also react on the Moon. The tides are slowing down the Earth, and they are also driving the Moon farther and farther away. This result, strange as it may seem, does not permit of doubt, for it is the result of an indubitable dynamical principle, which cannot be made clear without a mathematical discussion. Some interesting consequences follow. Since the Earth is slowing down, it follows that it was once rotating faster. There was a period a long time ago when the day comprised only 20 hours. Going farther back still, we come to a day of 10 hours, until, inconceivable ages ago, the Earth must have been rotating on its axis in a period of from 3 to 4 hours. At this point, let us stop and inquire what was happening to the Moon. We have seen that at present the Moon is getting farther and farther away. It follows, therefore, that when the day was shorter the Moon was nearer. As we go farther back in time, we find the Moon nearer and nearer to an Earth rotating faster and faster. When we reach the period we have already mentioned, the period when the Earth completed a revolution in 3 or 4 hours, we find that the Moon was so near as to be almost grazing the Earth. This fact is very remarkable. Everybody knows that there is a critical velocity for a rotating flywheel, a velocity beyond which the flywheel would fly into pieces, because the centrifugal force developed is so great as to overcome the cohesion of the molecules of the flywheel. We have already likened our Earth to a flywheel, and we have traced its history back to the point where it was rotating with immense velocity. We have also seen that, at that moment, the Moon was barely separated from the Earth. The conclusion is irresistible. In an age more remote, the Earth did fly in pieces, and one of those pieces is the Moon. Such, in brief outline, is the tidal theory of the origin of the Earth-Moon system. the day becoming longer. At the beginning, when the moon split off from the earth, it obviously must have shared the earth's rotation. It flew round the earth in the same time that the earth rotated, that is to say, the month and the day were of equal length. As the moon began to get farther from the earth, the month, because the moon took longer to rotate round the earth, began to get correspondingly longer. The day also became longer, because the earth was slowing down, taking longer to rotate on its axis, but the month increased at a greater rate than the day. Presently the month became equal to 2 days, then to 3, and so on. It has been calculated that this process went on until there were 29 days in the month. After that the number of days in the month began to decrease until it reached its present value or magnitude, and will continue to decrease until once more the month and the day are equal. In that age the earth will be rotating very slowly. The breaking action of the tides will cause the earth always to keep the same face to the moon. It will rotate on its axis in the same time that the moon turns round the earth. If nothing but the earth and moon were involved, this state of affairs would be final. But there is also the effect of the solar tides to be considered. The moon makes the day equal to the month, but the sun has a tendency, by still further slowing down the earth's rotation on its axis, to make the day equal to the year. It would do this, of course, by making the earth take as long to turn on its axis as to go around the sun. It cannot succeed in this owing to the action of the moon, but it can succeed in making the day rather longer than the month. Surprising as it may seem, we already have an illustration of this possibility in the satellites of Mars. The Martian day is about 1/2 hour longer than ours, but when the 2 minute satellites of Mars were discovered, it was noticed that the inner one of the 2 revolved round Mars in about 7 hours 40 minutes. In one Martian day, therefore, one of the moons of Mars makes more than 3 complete revolutions round that planet, so that, to an inhabitant of Mars, there would be more than 3 months in a day. End of chapter. End of book. Thank you for listening.